What is gradient descent and why is it called so? Suppose we have a cost function j theta. Think of it as a landscape. Some choices of parameter theta give large error, some give small error, and our aim is to find the lowest point. The gradient, which is denoted by delta of j theta, is a vector that points in the direction of steepest increase in the cost. Therefore, if we want to reduce the cost as quickly as possible, we should move in the opposite direction, that is downhill. That is called as descent. So, gradient descent is simply repeatedly taking a small step downhill on the cost surface until further steps no longer help. A good way to remember this is the gradient tells you which way is uphill, gradient descent walks you downhill. So the key idea can be denoted as theta equal to theta minus alpha times delta j theta. Now what is alpha? The symbol alpha is the learning rate. It simply means the step size. If alpha is too small, you move downhill but painfully slowly. If alpha is too large, you may overshoot the minimum and oscillate or even diverge. So alpha does not change what the best answer is. It changes how quickly and how safely we reach it or approach it. Now let's discuss about the convergence and the stopping criteria. We say that gradient descent has converged when further updates become negligible, when we are effectively at the bottom of the bowl. Common stopping criteria include the cost improves by less than a tiny tolerance. So the cost function is denoted by j. So j theta t plus 1 minus j theta t, that is the value of j theta at the iteration t plus 1 minus the value of j theta at the iteration t, their difference is absolute difference is less than epsilon. There is not much change in the cost. Or second, the parameters don't change much. The parameters barely move. So theta t plus 1 minus theta t, the change in parameters is less than epsilon. Or the gradient becomes very small, nearly flat. So if you observe in case of parameters and in case of j theta, we are taking norm because they are vectors. So delta j theta and delta j theta L2 norm is less than epsilon. The magnitude of this is less than epsilon. In practice, we also set a maximum number of iterations, so the algorithm always terminates. The steps of gradient descent in plain terms are as follows. First, you choose an initial guess for theta. Often it is all zeros. Second step is you compute the predictions y hat. Third step is you compute the errors y hat minus y. Fourth step is you compute the gradient of the cost. Then fifth step is you update theta using the learning rate alpha. And then you again go back to step 2, so that after changing the theta, what are the predictions y hat. So from step 5 to step 2, so you keep on repeating steps 2 to 5 until one of the stopping criteria that we discussed triggers. That's it. So why gradient descent feels like proper machine learning compared to whatever we have studied till now? See, first we studied closed form formulae for solving linear regression. They differ for increasing or like different number of predictors, right? So then we discussed about the solution, which is normal equation, which is x transpose x whole inverse x transpose y. Now this is more elegant than closed form formulae because the same thing works irrespective of number of data points you have and number of variables or number of predictors that you have, right? So it is elegant, and for small problems it's perfectly sensible. But gradient descent is truly machine learning because first thing is scalability. In case of the normal equation, we have to invert x transpose x. Now that is numerically expensive. Okay, and as our number of features increase, it becomes more and more computationally difficult. In case of gradient descent, we don't have to take any inverse. Second is the generalization or generality. Most real ML models do not have neat closed forms. Gradient descent and its variants extend to logistic regression, neural networks, and far beyond to other deep learning algorithms and so.